Good afternoon, all. I'm Alexandra, a Grant Innovation Ambassador, and today we're having a demo and discussion with our data science team on the models we are developing for healthcare. Let us welcome both Mr. Ash, founder of CertifAI Labs, and Mr. Joel, our data science intern. Welcome to you all. Let me start with high level
Thank you.
with Mr. Ash, and then we will go to demo with Mr. Joel. The first question going to Mr. Ash. What is the CardioGuard AI? And can you explain about the data science research and models you are building?
Yeah, thank you, Alex. Thank you, Joel. I'm audible, right? So, yeah, today, we are actually going to explain about our MVP. Basically, we are developing for our something called CardioGuard. This is actually working with a wristband, and it can monitor people for their health of their heart, and they can actually give indication proactively about the cardiac related illness, and then it can also do a lot of personalization, and then give diet recommendations, exercise recommendation, and then it can also watch if there are any irregularities in the BP. It can actually see the ECG, PPG, stress. All these things can be monitored over a period of time. And then using this data, along with other patients' data, we are actually training the machine learning models. We are developing some models, and then that is used for predicting, the heart health.
Okay, thank you so much for this question. So let's move on to the second one. To you, Mr. Ash, how can computers help us understand what causes heart problems?
Yeah, so once you have the data, right? So we have the data about the like irregularities, right? So these irregularities are being trained, for the uh, machines, and these machines are basically, they are actually learning the patterns of data from a problematic heart. It can be like patient information, including age, blood pressure, and habits, and even it can find patterns, right, that might be hard for doctors to see, right? So this will help to figure out, what things make heart problems more likely.
Okay, it's very interesting. So, what are the biggest warning signs in the data that someone might have heart disease?
Yeah, by analyzing the data, right, we can find out which signs are most strongly linked to heart disease, right? For example, data might show that chest pain during exercise, or certain heartbeats, that are could be a big red flag. Okay.
Okay. If there is a lot of information about the patient's health, how can we simplify it to focus on what most important to their heart?
Okay, yeah, that's a good question. So, this is something called the principal component analysis. It's a data science technology. So, computers can take all the complex data and then narrow it down, to certain key factors. They really matter to the heart health. So, this makes it easier for doctors to, understand and make a decision, right, about what can be the real cause. And that's the way, PCA is a technique, to identify the key factors or the principal factors which contribute to for their heart health. Back to you.
Okay, I see. So let's move on. Can analyzing health data helps doctors predict who is at the risk of getting heart disease before they even have symptoms?
Yes. So, in the case of a patient going to hospital, usually when there is a symptom develop, they go to hospital. But in this particular case, we have the wristband which monitors you 24 hours, and then it is studying your health and your health of the heart and all the data and the patterns. What are common things? What are normal things? These things are being compared, right? So we are now creating tools, and that can even spot, people who are likely to develop heart problems in the future. So this allows doctors to take some actions early and then prevent the serious issues. So you don't have to wait till the heart disease or heart attack to occur. By using our band, we can proactively know when the patient will go into or when the person is going to develop heart disease.
Okay, fine. And the last question, beside the usual things like age of cholesterol, what else can data tell us about why some people get heart disease and others don't?
Yeah, so data analysis, can reveal new risk factors, or it can have like a combination of risk factors, right? That we don't, usually we don't understand it fully before. So it will give some hidden insights about all these risk factors. This could be some subtle patterns like heart rhythms or how different factors interact with each other. So this is a way doctors can get a better insights, right? When the alarms are occurring, and these things can be done by machine learning models, right?
Okay, thank you very much. It was amazing.
Thank you.
So we are moving to questions to Joel, right?
Yeah, he's maybe doing a demo. Yeah, Joel, you can just share the screen.
Yeah, let me share my screen a second. Let me know if my screen is visible. Is my screen visible? Hello?
Yeah, it is visible.
Yeah.
You can make it bigger, I think. There's a
Yeah.
small button on the right side.
Yes. Okay, so yeah.
Yeah, you can continue.
Yeah,
Yeah,
got it. Okay, so like this okay, so I first of all, good afternoon, one and all, everyone present here. So today I'll be explaining to you like the assignments or the tasks that I have been doing in my internship. So basically the purpose of this internship was to give me knowledge on certain aspects, certain topics that are related to data science. So here, what I basically done is I have learned about PCA, the exploratory data analysis, the correlations, all that are very much important in before we go for modeling. So let in the next few slides, I'll be I will be showing you what all I have been, what all knowledges I have gained. So here, okay, here Now, this is the dataset that I have been working on is heart disease dataset. So basically contains the records of the patients. It's a real-time dataset that contains the records of patients. It gives the patient's age, sex, the chest pain. We can see there are 4 types of chest pain, like angina, atypical angina, non-anginal pain, and asymptomatic. And the cholesterol. So there are lots of features that are available in this dataset, like this one, fasting blood sugar, max heart rate achieved. These are datasets. These are the features that are there in the dataset. So first off, data preprocessing. So first, when we get the data, we need to preprocess the data before doing some work on it. So basically, what is data preprocessing? So data preprocessing is the process of cleaning, transforming, and organizing the raw data that is given to me into a usable format. Think of it like prepping ingredients before cooking. So the better the prep, the better the final dish. So first what we do is we check for the missing values. So I used in the Python code that I've been using, I used isNull.sum. That is a function that is used to check the missing values. So in this data set that I have got, there are no missing values found. So it's a good thing. Now we check, then at the next step, we check for the duplicate records. So there is a different function for that. It is called a duplicated.sum. So then when we found some duplicate values, we need to remove the duplicate records. Then we do the data type conversion, that is converting the categorical variables were needed using there is a function called .asType to category. Now, feature engineering is used when to create additional meaningful features based on the domain knowledge, that is on the heart disease. That is what. Now, the next thing I went through is multivariate analysis. So basically, what is multivariate analysis? It is a set of, I learned that it is a set of statistical techniques that is used to analyze data that involves more than one variable at a time. So the goal is to understand the relationship between variables and how they influence each other. So to put it simply, in simple terms, instead of looking at one factor in isolation, multivariate analysis looks at how multiple factors interact together. So the objective was to explain the relationship between between different variables. Now we can do multivariate analysis by plotting scatter plots or pair plots. So for example, to see the scatter plot, so relationship between age and cholesterol levels, that we can put in scatter plots. And one second. Yeah, okay. Now so for pair plots, relationship between key numerical features that we can do it in pair plots. Then we can do heat map visualization to see the multivariate analysis. So the heat map visualization, it identifies patterns between the correlated features using Seaborn's heat map function. So we can get so many information from doing a multivariate analysis. Let me show you one example. See, this is a screenshot of an plot that I have got when I was doing a multivariate analysis. So here we can say that the maximum heart rate is achieved when people undergo any physical activity that will increase their heart rate to a maximum level. The asymptomatic pain, that is the green points, it was mostly suffered by people with heart disease. Therefore, we can understand that most of the patients who were found to have heart problems were at an early stage and they experienced no chest pain. Now, let's move on to correlation analysis. So, what is correlation analysis? It measures the relationship between two continuous variables. So, correlation is a what do you say, like a statistical measure that describes the strength and direction of a relationship between two variables. So in simple terms, when one variable changes, how does the other change? That question will be answered with the help of correlation. So there are two types of correlation used, Pearson correlation and Spearman correlation. So Pearson correlation, it measures the linear relationships, and the Spearman correlation, it measures the monotonic relationships. So yeah, why correlation is important? So correlation is important because it helps us understand the relationship between two variables. For example, like studying more might lead to better grades, right? It's especially useful in data analysis and machine learning, where it helps identify which features are useful and which might be not that useful. By spotting strong correlations, we can simplify models, improve accuracy, and avoid problems like multicollinearity. Correlation is also widely used in fields like business, healthcare, of course, and finance to make smarter decisions based on the data trends. Now, okay, so to look detail on the Pearson correlation, it is the mostly commonly used type of correlation. So, in statistical terms, the Pearson correlation, that coefficient, it measures the linear relationship between two continuous variables. So if that coefficient, it's perfect for if it is like +1, it is perfect for positive linear relationship. And if that coefficient is like -1, it's perfect for non-negative, it's negative linear relationship. And if the coefficient is 0, it means there's no linear relationship. So we use it when to use Pearson correlation. If you ask, we can say that if the both variables are quantitative, we use Pearson correlation, or if the relationship is linear, we use Pearson correlation. And also, if the data has no extreme outliers, then also we use Pearson correlation. Now, okay, so take an example. Like here, you can see the hours studied and the exam score. So we can see that there's a strong positive Pearson correlation, since more hours means higher scores. Now, this is a screenshot that is from the findings. So what we can see from this is that this is a Pearson correlation that I have done. It's a heat map. So here we can say that the higher correlation between THALAC, that is the maximum heart rate, and the heart disease. So there's a high correlation between them. Now, there's a moderate negative correlation between age and THALAC. So similarly, we can find more insights when we put the heat map. Now, let's go to the Spearman correlation. So Spearman correlation, so to talk more about Spearman correlation, in statistical terms, the Spearman correlation coefficient, it measures the strength and direction of the monotonic relationship between two variables using ranked data. So what is monotonic? It's a relationship is monotonic if it is always increases or always decreases, but not necessarily at a constant rate. And now Spearman correlation, it's a non-parametric test, meaning it doesn't assume that data is normally distributed. So and also the Spearman correlation, it works well when data is ordinal, or when relationships are non-linear but consistent in direction, monotonic. Now, how it works. Actually, it converts the data into ranks in a rank order, giving them ranks on the data, and then we apply the Pearson correlation formula to that ranked data. That is how Spearman correlation works. So yeah, and when do we use Spearman? When variables are ordinal or not normally distributed, we use Spearman. Otherwise, we use Pearson. And if you suspect a non-linear but still monotonic relationship, then also we go for the Spearman correlation. And if in the data there are outliers are present, then that could distort the Pearson's correlation coefficient. So then also we go for Spearman correlation. That is on Spearman correlation. Now, okay, so this is an example heat map that is of Spearman correlation. So here we can say it's similar to Pearson, but it detects non-linear relationship. Now, some variables showed stronger ranking correlations. Okay, yeah, this is a table that gives the differences between Pearson and Spearman. So we can see Pearson is parametric and Spearman is non-parametric, linear, and the other one is monotonic. And yeah, the main thing is Pearson is sensitive to outliers and the Spearman is not. Yeah, and so the key findings that I got from um, the project that I have to, I'll show it later in the coming slide. So the main key features, key findings that I got from by using correlation is that these like feature selection can be like refined based on correlation and so on. So there are some kind of key findings we can get from performing correlation on the data. Okay, now I'll walk you through how I used principal component analysis or PCA to make hard disease prediction models more efficient, and how I applied explainability tools like SHAP and LIME to build trust in these models. Okay, so PCA helped me simplify the models by transforming the original features into smaller set of components without losing much of the variable information. So this made the model easier to train and interpret. That is the basic use of using PCA in our code. Okay, here's like a 2D projection of our data after PCA. So each point is a patient. Okay, and we can already see some separations between the higher and lower risk individuals based on just the first two components. Now, okay, now this plot, it shows how variance is captured by each principal component. We found that just 10 components preserved most of the data's complexity, making it efficient for modeling. And now, okay, now about PCA. Now, while standard PCA worked well for our dataset, we use standard PCA only. There are other useful variants depending on the use case. Now, the sparse PCA, it's particularly useful when we want to improve interpretability. It forces some loadings to 0, making it easier to link components to specific features. It's almost like feature selection. Then kernel PCA, it extends PCA by using kernel tricks to handle nonlinear relationship, which might be useful in more complex biological interactions that linear PCA can capture. And incremental PCA. So for very large data sets, the incremental PCA allow us to run PCA in smaller patches, making it much more memory efficient. Yeah, these are the about the PCA, different PCA and we use their benefits and such. Okay, now beyond simplifying models, PCA helped us discover new patterns. For example, clustering on principal components revealed different risk groups useful for tailoring interventions. Yeah. In fact, okay, so with fewer features, my model trained faster and for like less prone to overfitting. It also helped highlight which aspects of patient that were more predictive, you know. Okay, now SHAP, as told earlier, like SHAP lines the shapely adjective explanations. It is a powerful method used to explain the output of machine learning models. It provides insights into how individual features or like inputs contribute to the model's predictions, making the model more interpretable and transparent. To simply put it, SHAP is a method that tells us how much each feature pushes a prediction toward higher or lower risk. It's helpful in identifying key risk factors in an individual prediction. And similarly, LIME also. LIME means a local interpretable model agnostic explanation. It is another popular method used to explain the same machine learning model predictions. LIME actually helps make models more interpretable by providing local explanation, meaning it explains why a model made a certain decisions for an individual prediction. Like to simply say, a LIME builds a simple model around one prediction. It gives it gives the doctors an easy to understand explanation of why the model flagged a patient as high risk. And yeah, thank you. And yes, thank you.
Thank you so much. We have 2 minutes left in our session, but I will ask some questions. I have questions. So the first question, Mr. Joel, would be, could you elaborate on the specific data processing steps you took before applying to PCA? For example, how did you handle scaling and why did you choose your method?
Okay, so before using PCA, I cleaned up the data. So for missing numbers, I use the middle value, and for missing categories, I use the most common category. Then I changed the categories into numerical format that the computer can understand. After that, I scaled all the numerical values so they were on the same playing field. I did this in the way that makes it easier for the computer to compare the values.
Okay, in your PCA implementation, how did you determine the optimal numbers of principal components to retain, and what were the criteria?
Okay, to figure out the best number of principal components, I used a couple of methods. First, I checked how much of the data's information each component kept. I chose the number of components that kept most of the important information, like 95%. Second, I looked at the graph that shows how much each component explains. I looked for the point where adding more components didn't really add much information. So basically, I want to use a few components as possible while still keeping the data's main characteristics.
Okay, good. When you're performing correlation analysis, did you consider any nonlinear relationship between variables, or did you focus solely on the linear correlations?
Okay, so I mainly focused on linear relationships, which are most straightforward. But I also looked at some graphs to get a feel for the data and see if any relationships looked non-linear. In the future, I could use more advanced techniques to check for non-linear relationships.
Let me also ask a couple of questions.
Yeah.
For the exploratory data analysis, right? So,
okay.
Could you provide some more details on how you handled the outliers in the data set? And how do you, see the impact in your overall analysis?
Okay. So during EDA, I look for data points that were very different from the rest. So for example, I saw that some patients had very high cholesterol or like blood pressure levels compared to others. So basically, outliers can cause problems because they can throw off the analysis and make it harder to accurate results. So what I did was I dealt with them by noting them and what they were, try to understand if they were real or just errors. So maybe in the future, I could use some more advanced techniques to reduce the impact of outliers.
Okay, good. Thank you. And yeah, one more last question. Okay, so now in the context of applying PCA, how do you assess and conclude, the resulting components, principal components, especially, the relation to the original features?
Okay, so in order to understand what the principal components mean, I looked at how each of the original measurements contributed to them. So if a component was high values of like age, blood pressure, and cholesterol, for example, it probably relates to overall heart risk. So I also used my knowledge of heart disease to make sense of what the components represent. In the future, I could use some methods to explain how these components affect the predictions as well.
Thank you. So yeah, so thanks a lot for both of you. And one more, final, your feedback. How was your experience, about the internship, and what is your suggestions for, people who are coming new?
Mm, I would highly recommend this internship at CertifAI. So, like my internship at CertifAI was really like a positive experience. What stood out to me was like how well organized and supportive everything was. So, like we had regular check-ins, one in the morning and one in the afternoon. It helped a lot in staying on track with our task and made it easy to ask for help if we were stuck on something, like maybe one task. And we also kept like a timesheet to log what we were working on. So, which I found helpful for staying focused and being aware of my own progress. The mentorship was great too. Like everyone was approachable and always willing to guide or give feedback. Overall, it was a great learning experience where I felt like I was growing, not just technically, but also in how I work and communicate in a team.
Thank you for your
Yeah.
feedback, and I hope you
Yeah.
all the best for your job and other things.
Yeah.
Thanks a lot. Thank you.
Thank you.